Hello everybody, welcome back to another video, and in this video we'll be continuing on for my series of looking at the derivatives and the integrals of the inverse trigonometric functions, where in today's video we look at the integral of the inverse cosine of x. And by doing that, we'll need to know what the derivative of the inverse cosine of x is, so I would have made that in my previous video, and in fact the working is all here. So what we need to do often when we are taking the integral of a single function in which we don't know how to integrate, of course, we need to use the idea of integration by parts, where we see that this function is the same thing as this function multiplied by 1. And we know that if we have a product of two things in an integral, we can use integration by parts. So for that, we'll be using the DI setup. And in the DI setup, we set up a column to differentiate something and set up another column to integrate something. So here we'll have a plus and a minus. That is how the DS setup works, and this is exactly the same thing as integration by parts. However, it is just a more visual and easy way to work with when you're doing multiple layers of integration by parts, because all we have to do is we need to see that when taking the derivative, so let's say we obviously want to take the derivative of the inverse cosine of x, because that's what we know how to do, and we taking the integral of 1, because we see that this original product is the integral that we're trying to find out. And remember that the product of a row is always an integral. So this is the integral we're trying to find out. And what we need to do is we need to just take the derivative and the integral respectively in each column. So let's take the derivative of the inverse cosine of x. So that is going to be the negative of 1 over the square root of 1 minus x squared. So that is what we got in our previous video. And let's take the integral of 1 in the x world. Yes, that is just our favorite thing to do, 1. So what we see in the DI setup is whenever we have a row remaining where we can take a product, before that we need to take the product of the diagonals. So we need to take this, and then we need to take this as an integral. So we know that the row is always an integral. So this, just to make it clear, is with this. So what we do, we take the product of the diagonals. So here we have the inverse cosine of x multiplied by x. So we see that the integral, we can write it, of the inverse cosine of x is equal to, then we have x multiplied by the inverse cosine of x. Then we have a minus and a minus here. So that is going to make it a positive, because remember that we are now subtracting the integral of negative 1 over 1 minus x squared multiplied by x. And taking the negative out, the negative and the negative make a positive. So here, because we know that in the traditional way we have uv minus the integral of v du, so that corresponds to this negative that is in this other column of these signs. So here we just have a plus now because there's a negative here. Then we have the integral, and then we have just an x over the square root of 1 minus x squared dx. And this is the exact same integral that we had to evaluate in our previous video, because what we do now is we can just see that we have an x squared in the denominator, and here we have an x, and that very nicely happens to be the same degree as the derivative of x squared. So what we can do is we can take a u sub, where we said u to be 1 minus x squared. Then taking du, we see that now taking the derivative of with respect to x on both sides, we get du, and then taking the derivative of 1 minus x squared, derivative of 1 is 0, derivative of minus x squared, that's minus, and derivative of x squared is just 2x, just our favorite power rule, then multiply by dx, and then we need to isolate dx now, so we see that dx is equal to negative du by 2x. And what we see here is that this is really the same thing as negative 1 by 2 du by x. So we can take this negative 1/2 multiple out of the integral, and we see that this is equal to x times the inverse cosine of x, and then here we have a negative 1/2 multiple that we've taken out. So that negative with this positive will of course make it a negative, and then we take the half out, and then we have the integral of x over the square root, and then 1 minus x squared is our u, because we're trying to get everything to the u world, and our dx that we solved for is negative 1 by 2 du by x. We've taken that negative 1 by 2 out, so we're just left with a du by x. And here, very nicely, we see why this u sub worked. This x and this 1 over x will cancel out very nicely, and all we're integrating now is, so we just have now x times the inverse cosine of x minus 1/2 multiplied by the integral of 1 over the square root of u du. And here, of course, we know that the square root of u is the same thing as u to the 1/2. And we know that a to the negative n is equal to 1 over a to the n. So if we use the reverse of the idea and we see that we have 1 over u to the 1/2, that must be where our n is 1/2. So we must have this being equal to u to the negative 1/2. So all we're doing is we have x now multiplied by the inverse cosine of x minus 1/2 of the integral of u to the negative 1/2 power du. Everything is in the u world. And what we do now is we see that we have a negative 1/2, and that is just a constant. So what we can do, we can use our favorite power rule, where we now take u to the n plus 1 over n plus 1. So that would just mean taking u, then add 1 to the power, and divide by that new power. So that's equal to x multiplied by the inverse cosine of x, all of the same stuff, multiplied by 1/2, and then let's evaluate this. So let's add 1 to the power. So 1 plus minus 1/2, it's just going to be, of course, a half. So our new power is 1/2. So we have u to the 1/2. We have u to the 1/2, and then we have to divide by the new power. So we're dividing by 1/2, and dividing by 1/2 is, yes, the same thing as multiplying by 2, because you're taking the reciprocal of 1/2, which is 2. So now we just have 2u to the 1/2. And what we see here is that this 1/2 and this 2 multiple cancel very nicely. So what we have is just now the x inverse cosine of x minus u to the 1/2 power. Now all we need to do to get back into the x world is we have to substitute what our u was. So we finally see that the integral of the inverse cosine of x dx is just equal to then x multiplied by the inverse cosine of x minus, and then our u was 1 minus x squared, and the half is the same thing as the square root, so we can just take this as the minus the square root of 1 minus x squared, and here we can put a plus c because we are done. So this is our answer to today's video. And something interesting that I will showcase here is, and then I'll bring up a question, what is the integral of the derivative with respect to x of some f of x, and that integral is all with respect to x. So what would happen here? Well, of course, the derivatives and the integrals would just cancel out, and you'd just be left with f of x. So what happens if I ask you to take the integral of the negative of the 1 over the square root of 1 minus x squared dx? So we know, first of all, that by definition, what we've just looked at in our previous video, the derivative of the inverse cosine of x is negative 1 by the square root of 1 minus x squared. So this is equal to the integral of the derivative with respect to x of the inverse cosine of x, and that integral is with respect to x. And what we'll see, these cancel, and you're just left with the inverse cosine of x. And you can here, in fact, put a plus c because this is indeed a valid answer to this integral. Now, what would happen if we took this negative sign out? Because we know that we can do that with integrals. So we see that this is also, so let's put an or. This is equal to the negative of the integral of 1 over the square root of 1 minus x squared. Now here we have another definition of one of the derivatives that we know. This is equal to the integral of the derivative of the inverse sine of x now, because that is the derivative of the inverse sine of x, in fact, with respect to x. You see that this, and then we still have a negative here, this and this and this and this will cancel, and we're just left with negative, and then the inverse sine of x, and we can put a plus here as well, because I will tell you that this is also a correct answer. So what is going on here? Because by definition, we're taking the integral of one function, and then as a result, we're getting two different functions. So does that mean that those two different functions are equal? Well, that is actually the case. However, this is a specific case where they differ by a constant. That is a key thing, that the answers, so I'll just write this like this, the answers diff by a constant. And that is, of course, because of the very famous identity that the inverse sine of x, so let's just write this here, the inverse sine of x plus the inverse cosine of x, inverse cosine of x is equal to pi over 2. And I proved this in my last video where we looked at the derivative of the inverse cosine of x, and this all comes from the reason that the sine and cosine are cofunctions, and therefore the angles are complementary, which means that they add up to pi over 2 radians or 90 degrees, and therefore if you set up a system where you set the inverse sine of x to be some theta, then the sine of theta, which is the same thing as cosine of pi over 2 minus theta, if you take the arc cosine and then on both sides see that the angle is within the correct bounds, so you can cancel them, and you see that you get a case where you get theta plus pi over 2 plus pi over 2 minus theta. These will cancel and you're left with pi over 2. That is just a quick rundown of the proof, but you can see my previous video for the full visual explanation. Now here, what we see is that if we subtract the inverse sine of x on both sides, we see that the inverse cosine of x is indeed equal to pi over 2. So I'll write it like this. It's equal to minus the negative of the inverse sine of x plus pi over 2. Now what we see is that this function part is equal to this function part. However, we just have a plus pi over 2, so that is where the term differs by a constant comes from, because here we see that these are indeed equal, however they just differ by pi over 2. So what we can really do is we can see that you can combine this pi over 2 with this plus c, because this plus c is a constant of integration. Pi over 2 is just another constant, so eventually you see that you can join all of them to become another c and see that they are indeed equal. So in the terms of indefinite integrals. So that was it for today's video, and thank you for watching.